Okay, let's start. So we have done current mirror last class. Okay, so we have done until we find what is the IREF required. So let's go to passive and active current mirror. Okay, so for passive current mirror, what does it mean by passive as in? So first point, the current mirror, CM is current mirror over here. I know it's sometimes confusing common mode current mirror, but CM over here is current mirror. It is connected to the output only as a load. What's a load mean? Like it is acting more like a resistor instead of it is helping to bias. Because usually we use current mirror to bias the circuit. But in this case, we are not biasing the circuit, but we use the current mirror as a load on it. So you can see V in 1, V in 2, M1, M2. If without the top part, it looks like a differential amplifier. But once we have added this current mirror at the right-hand side, now this seems like a resistor that we add usually on top of our M2. So this is the load. Now we can say V out is controlled by V in. Okay, there's no relationship between IREF and V out. Okay, there's no, basically IREF is not controlling my V out a lot. It's directly controlled by V in. The output over here is controlled mainly by your V in. So this current mirror over here is passive. So it is not very useful because it has no control to the output. But in some cases, we might need this thing, okay, to control the resistance. But the other type is active current mirror. So active current mirror is more important, is the one that you might need to use in your assignment, that usually you will need to use to bias your circuit. So active current mirror, we say that the current mirror is directly connected to the circuit. Directly connected to the circuit. Okay, so you can see the current mirror is placed directly on top of my differential pair. So now IREF is produced by V in. So whatever V in over here, you control your M1, then it allows some current to flow through. So that's your IREF. IREF produced by your V in. And since it is produced by V in, it will also control your V out. That's why we call it active current mirror, because it is actively controlling your V out. So in this case, current mirror has some effect on V out, and it is a varying effect. Okay, you change some part of your current mirror, it will change your V out. So this is more important. We will look more detail into it. First of all, let's see the first case. When V in is equals to 0, and when V in 1 is equals to 0, and when V in 2 is kind of increasing. Okay, so this is 0, this is increasing. What will happen? When M1, V in 1 is 0, M1 will turn off because the gate is too low, so it will turn off. But M2, there's something there, so M2 will turn on. So if M2, so at this time, if M1 is turned off, will there be any current for IREF? There won't be any current for IREF because my M1 is turned off, so no current is generated from here. Then there's nothing from your M3. If there's nothing for M3 current, they're in series, so there's no IREF. So your M3 is basically off. If M3 is off, since this is current mirror, M4 will copy the behavior of M3. So M4 will also turn off. So in this case, you can see when V in is 0, V in 2 has something. M1 turns off, M2 turns on, 3 and 4 also off. In this case, there's no current flowing over here. So basically, you do not have any V out. Because here basically open circuit already. You do not have any V out. We can say V out is equals to 0 because powering up M2 alone is not useful. The first case, okay? The second case, when you increase slowly your V in 1, near to V in 2 already, so both are turned on. So since both have current, when M1 has current, your M3 will also have current, so M3 will turn on. If M3 turn on, M4 copy M3 behavior. So M4 will also turn on. And then my M2 also turn on because Vin 2 there is something. So now all 4 transistors turn on. We also say that important one is Vin 1 turn on, so it will generate ID1. This ID1 will become your ID3 because that's the reference current. This reference current will flow into your ID4. ID4 copied by ID3. But ID4 and ID2, they are in series. So now ID2 will be the same as ID4. So 4 IDs are the same now. So we say that Vn is equals to VDD minus VSD3. So you can see Vn is over here. It's equals to VDD minus V source drain number 3. This is PMOS. So source to drain. Basically, it's your source to gate as well. So Vn is equals to VDD minus this point. It is true. And V out is equals to VDD minus VSD4. V out is equals to VDD minus the drop over here, right? So source to drain of M4 drop. So we are examining what is V out. So let's see what is V out from this formula. You imagine that if your ID4 going down, V equals to IR, so your VSD4 also going down. What happens to your V out? Your V out will increase. So as the current decreasing, your V out will increase. So we can see a graph. Okay, so here is V out. Here is V in 1 minus V in 2. V in 1 minus V in 2. Okay, meaning that initially V in 1 is turned off. That's why there's no output. And then slowly when you increase V in 1 already, your output supposedly be increasing. Supposedly be increasing until VDD. Okay, so you can see from this equation. So here V in 1 slowly approaching V in 2. So V in 1 minus V in 2 from negative is slowly go up. When it slowly go up, then your V out is actually increasing. Okay, why is it increasing? Is because your VSD4 is decreasing. So if you see V in 1 minus V in 2, if they are equals to 0, when they are exactly the same, there should be around half of VDD only. When V in 1, V in 2, they are exactly the same, the V out is only exactly half of it. Okay. Next is if my V in 1 increasing, V in 2 turn off. So when V in 1 is turned on, for sure 3 is turned on. When 3 is turned on, 4 copy 3. So 4 will also turn on. But M2 turns off. So in this case, we can say ID1 is equal to ID3. But because I2 is 0, that current is supposed to be 0 at ID4 as well because they are in series. So now ID4 is not equal to ID3. So we say V out is equal to VDD minus VSD4. But since ID4 is equal to 0, okay, so VSD is also equal to 0. That's why your V out is equal to VDD directly. Okay, if you're confused, you just need to remember the first and the third case. If they are connected in this way, So when Vin 1 is slowly increasing, that should connect, slowly go up directly. They need to connect this gap. That's why it will be a straight line without going up, slowly increasingly. Is that okay? Okay, if that's okay, I'm not very sure if it is okay, but let's say it is okay. I want you guys to find V out, because you cannot see it very much from the graph, from the explanation. We need to find out what is the small signal model, and then we want to find what is V out over V in 1 minus V in 2. So let's figure out what is V out divided by V in 1 minus V in 2. From this circuit, I want you all to do using small signal model. Okay, this one will take a lot of time. You try to do it. Okay, I'll give around 15 to 20 minutes. So draw out the small signal, see what happens. The VB over there is just a bias voltage, so it's a DC. You know that you can cancel the DC out. And take note that the top is PMOS. Okay, you need to draw a very complicated small signal model. So we know that for PMOS, it is one line on top, two line below. So we draw one line on top, two line below. For the first one first, we go part by part. Okay. Then usually in this case, we will see what happens at the source, what happens at the drain. Okay. Okay, sorry, I left off one. I connected here. Right. So we go part by part, we check how do we draw this, yeah? So this VDD is supposed to be grounded. So your source is basically grounded. So over here, we can just draw it is grounded. Okay, and then we know we will need a source. It's called GM3 VSG3 because it's a PMOS. So we use VSG. Okay, we don't do body effect because it will be very complicated. We can use maybe your channel length modulation only. Okay, so sometimes we will draw like that, but in this case, maybe it is not so smart to do it this way. Okay, we will see why. So you can imagine that if we complete it, the gate and drain is connected. So you will connect your gate and drain. Okay, if we say we consider channel length modulation, then usually at the right hand side, we will draw R03 over here. Okay, this is your source. So this is your source number 3. This is your gate number 3. This is your drain number 3, usually this way. So we have done for M3 generally. At the same time, we try only to draw M4. M4 also the same thing. Supposed to have one line on top, two line below. And then it will have GM4, VSG4. And then we will need a resistor, R0. Again, it is connected to ground. What happens is the gate and the gate is connected, or the gate and the drain is connected. Okay, the gate and the drain is connected to M3. So this is your gate. Okay, so you can directly connect to here. That's okay. And then your drain, we haven't connect somewhere. So that's also fine. Okay. But in this way, maybe some part will be floating. Okay. Maybe the connection is not that nice. Maybe the connection is not that nice. Now here is your VSG3. Here is your VSG4. Okay, if you maintain this way, it is also okay, But some people would like to have, since here already written their gate and gate are close to each other, so they will swap this thing so that the gate and gate they are close to each other. Okay, although here I'm still connecting to my drain to my gate, it is still look correct, but some people might want to move things around. Okay, so maybe we can keep it this way. That's okay. Then we continue. See, this is NMOS. We haven't connected the drain, so the drain and the drain still something missing, and this is your drain. This is your D4. This is your S4. This is your G4. Okay, so this drain is basically your V out. Drain is basically your V out. What happens at the gate at M1 and M2? M1 and M2 there are NMOS. So 2 lines on top, 1 line below. And let's just draw this first. GM1, VGS1 with R0. Okay, and then at the same time, the gate VGS1. This is your gate number 1. So this is your V in 1. We cannot ground V in 1. It's an AC source. At the same time, here source is a VP. Imagine if V bias is grounded, will you still have M5 power on? No, because this V bias is already off. V bias, this VB is already grounded. So basically ground and ground, that is not enough to turn on the threshold at all. You can consider VP as just a virtual ground. So this part is basically cancelled out. You can say this part is basically your VP. So this source is basically your VP. This source is just your VP. But we don't write that first. We draw another one first. Okay. This is your drain, number one. This drain, it connects to the gate and drain on top. So it's just this line. You just draw it upwards. Then we draw the other one. Okay. So here is the other one that I do not like to draw this way. Usually we say this is gate, drain, source. But you see during the diagram, my gate is at right hand side. I like to keep it right hand side. I want to keep it outside. So maybe I can keep this as my gate number 2. This is my drain number 2. This is my source number 2. Okay. Source and source, we know they are connected, M1 and M2. So we can straight away connect that. And then usually at the drain to source, only we will have the current source. So we draw it the other way around. This is my GM2, VGS2. And my R0 is over here. R01, R04. This gate is your VIN2. Here is your VGS2. And here, you just write it as a virtual ground, VP. So what happens at your drain? Drain is connected to V out. Okay, that's why I say this part we might want to swap. So this gate, this drain is V out, but it's okay. We just connect them here. So this is your full circuit model. This is your full circuit model. Now you can try to derive V out over V in 1 minus V in 2. See what is the answer. Okay, now you take your time to slowly derive. Your answer is very, very complicated one. So if you see a lot of GM, BM, all those, you can check. Okay, the answer in the end, it will be okay. You can first assume GM1 is equals to GM2. We call it GMN. And then GM3 is equals to GM4. Is equals to GMP. R01 equals to R02. We can call it R0N. R03 equals to R04. We call it R0P. Yeah, you can assume all this first, and then you will get your answer. This is your answer. Okay. If you assume this to be very small, and then you can get GMN R0N parallel R0P. Okay, so this is supposed to be your answer. You can have all the steps figured out.
正在连接。已解锁，请取出话筒。已上锁。
Okay, I just told them, from our syllabus, I suppose we don't really need the class replacement. I won't be around 19th of June. So we're supposed to replace one class. So if you guys don't mind, and I don't think you guys mind, and if you can finish our syllabus, so maybe we don't need to replace the class. Initially, we said we will have class until 12:30 and then 1:30 onwards, right? Today. So we don't need to have that. Okay. Okay, so maybe we do part by part. First, we can see there are a few notes. Okay, there are a total of only 3 notes. Okay, we see from the board. So there are total only 3 notes. This is one note. This is the other note. And VP is one more note. Okay, VP is just a virtual ground, so VP is still important, yeah? So in this case, we call this note Vx. VP already got, this is basically your V out, so we don't need to call anything. Okay, but take note that we are dealing with current mirrors, meaning that the current flowing from M3, it will go down to your M1. At the same time, the current that go from M3, supposingly it goes to M4 directly. So we are copying the current. So we can use this advantage. Okay. First, if this advantage, can we say that whatever current that flows down from M3, we just model this whole thing as a resistor, also can. So we model the M3 as resistor first. If you want to model M3 as resistor, okay, we can just call it RD, let's say. We call it RD. So we take this whole part, yeah. We just call it RD. Okay, we will discover what is RD later, that's okay. Okay, we will discover what is RD later, that's fine. But if you can see on board, it is RD equals to R0 3 parallel with 1 over GM3. Okay, because here is your output basically. When we say we are seeing from the so when we are seeing from drain to source now, because it's PMOS, so it will be 1 over GM, the R, and then this will be your R0 3. So this RD, we can just model them into one over GM3 parallel with R0 3. So we see this whole thing as a resistor, that is enough. Meaning that there will be a current flowing down. What will be this current? So you can see this whole thing just as a resistor that connects to ground. This is RD. So if this way, we totally ignore the left-hand part already, this circuit becomes slightly simple. Now at node X, can we say that once the current that flows through node X, at this point, meaning it is 0 minus Vx divided by RD is your current. Because we assume all current flowing downwards. So top is 0, here is Vx. So 0 minus Vx divided by RD is the current that flowing down. So first, at Vx, not Vx, okay? We say that 0 minus RD divided by Vx is the current that flows down. It flows to where? It will flow to this part. So this part very straightforward. If it equals to GM1, VGS1 plus Vx minus Vp divided by R naught 1. Vx minus Vp divided by R naught 1. So that's your first equation already. This is your first equation already. Okay, we can rearrange a little bit and make the equation 0. So we can say 0 is equals to Gm1 Vgs1 plus Vx minus Vp R naught 1 plus Rd, 0 minus Vx over Rd plus Vx over Rd. So that's our first equation. That's all for Vx. Now we go to note V out. At this note, what will happen is, remember we say current mirror. So whatever that flows at your Vx down at M3, it will flow to your V out node as well. So we can say that the current that flowing from Vx Rd, Vx over Rd over here, it will flow directly to this part as well. Okay, it will flow directly to this part as well. So we can say that Vx over Rd. So we assume this is the current that flows down. Yeah? So the current that flows down, we say it is, so we have one Ix over here. Yeah? So since Ix is the same as V out, so we can say Ix is equal to what? The current that flows at here. So the current that flows at here, it is your Gm4, Vsg4 plus 0 minus V out. So we just say it's negative V out over R naught. So that's your Ix. Next is at node Vp. Okay. Actually, until this part, any question? Okay, maybe we say what exactly is your Ix? What exactly is your Ix? Ix is just Vx divided by Rd. Okay, although it's going down, but you can see this is grounded. Okay, so if we just move it down, basically the current that's supposed to flow here is just Vx over Rd. So Ix, we just say it is Vx over Rd equals to Gm4 Vsg4 plus, so minus, okay, minus V out over R naught 4 directly. And then finally, we investigate what happens at node Vp, the port that combines everything. So at node Vp over there, we can say that there will be number 2, there will be number 1 adding up. Okay, there will be number 2, number 1 adding up. So what exactly is happening at number 2? Number 1, sorry. What exactly happening at number 1? You have a current that flows down. Just how we say there will be a negative 0 minus Vx divided by Rd flowing down to this side. So we can say the same current will flow down to M1. So we don't really need to model M1 for now. Okay, we should model it as negative Vx over Rd, the current that flows to Vp, to the from top to the right left hand side of Vp, and then the one that flows from Gm2, we can say it is plus there will be a current flowing GM2, VGS2, plus V out minus VP divided by R naught 2. So all the current add up needs to be equals to 0. All the current add ups needs to be equals to 0. And what exactly is your VSG4? VS, this is your source, is 0. Gate is your VX. So we can say VSG4 is negative VX. And then from here, you can do all the maths already. So this is your equation number 2. So if we rearrange this, we take out VX. We take out VX. Okay. Your Vx will be equal to negative V out. So this is your equation number 2. And this is your equation number 3. Now you can substitute everything in. Our aim is to eliminate VP. Our aim is to eliminate VP. Okay, so the equation is very, very long. So you can substitute part by part. First of all, you take is equals to 0. So you take equation number 1 directly to 0. So this whole equation, you copy down the whole thing is equals to number 1. This whole equation you move down is equals to number 1. And then it will be very long already. And then afterwards, you can categorize them. And then you need to substitute VP and also VX. So you substitute all the VX in. So I will just copy down and then you see if it makes sense. Okay. So basically, you end up at here, it is already good enough. End up at here, and then you get the answer there already. So roughly have a look before we proceed to the second last chapter. Okay, I just want to confirm your grouping, yeah. So, Bie Liangyu, Liu Wentong, and Gao Changjian, one group. Correct? Any other additional people? Where is Changjian's name? Okay. So this is group number 1, I assume. I will just group according to colors, maybe. Okay, the next group is I think there's one more additional people, right? Hong Yuxiang, Chen Yaozu. What's your name? Sorry? Yeah, and one more people in your group, right? This one. Okay. So Xie Jiakai, Yan Shuyang, and Deng Jingxuan. Any additional people in your group? So both Chen Hao, same group. So Tomiko, you are in which group? You cannot do this alone. Who is Hu Xianzhe? Hu Xianzhe. So anyhow, so only 2 people that doesn't have group. Tomiko, please find your group. Join any of them by today. You text me by tonight telling me which group you're in. Please ask them or anything. And I will text Hu Xianzhe. If you guys don't get the group, I don't accept individual submission. Okay, so let's go to chapter 5, frequency response. I think at the very, very beginning of the chapter, at chapter 1 last time, when we want to draw the MOS device model, we say that it looks like this, but actually because there are metal, and then there are metal everywhere, and then there are dielectric oxide somewhere in between. So it actually forms some capacitors somewhere here. So we say that we will discuss that in subsequent chapter. So here, this is the chapter. Before we really go into what exactly are the responses of this amplifier, we know that high-speed circuits are everywhere. There are 2.5 gigahertz, 5 gigahertz, you know, your Wi-Fi. So all these high-speed circuits are everywhere, but can it be faster every time? We know that 2.4 is for sure worse than 5 gigahertz. 5 gigahertz response is very good. But can we do faster circuit every time? What is limiting it? The main thing that is limiting it is capacitor. Capacitor is limiting it. So for example, if we have a very, very simple circuit, just an RC network, we have our Vin, and then we want to measure what is the output of this capacitor. We will say that V out of this capacitor is equals to Vin 1 minus exponential negative T over RC. This RC is equals to your tau. Okay, so this RC, because of this C over here, of this capacitance over here, the V out will be slowly going up only. Okay, so we want V out equals to V in ideally. So we just want V in equals to V out, meaning V in times 1 directly. But now it is minus by this thing. So it is slowly going up. So you can see now your circuit, instead of just a step from 0 to 1 directly, when V in is 0 to 1 directly, your V out will need to slowly pump up. Slowly pump up, then only it can reach V in full equation. So if we want to improve speed, we have to minimize this RC. We need to make this as small as possible so that your negative T is as big as possible, so you can eliminate totally your exponential part. Then the next circuit is still not amplifier. We haven't touched into MOSFET yet. The other example. So if you want to measure V out, okay, if we model your capacitor as just an impedance, model it as a resistor instead, we can say the impedance of your capacitor, Z, is equals to 1 over omega C. 1 over omega C. So if 1 over omega C, we say that if you use normal voltage divider rule, I want to find what's happening at V out. So ZC divided by ZC plus ZR will be your V out times V will be V out. So let's see slowly what happens if at low frequency, at very low frequency, so omega is very, very low. So if bottom part is low, your overall ZC increases. So if ZC increases, meaning that it actually blocks a lot. But similarly, if your omega increases a lot, your Z overall decreases. So it already proved that supposingly you will have maybe a very, very nice graph initially, but as frequency goes higher and higher, when your omega goes goes low, okay, when your omega goes low, your impedance increases. So this increases, everything increases, then your V out actually very big at low frequency. But at high frequency, your Z goes down. So when ZC goes down, this ZC plus R1 goes down, everything, your V out goes down. So the whole voltage attenuated. that becomes lower. It's because of the impedance. Okay, because you just imagine capacitor impedance is 1 over something, C. So it's due to this 1 over, everything be inverted. So at high frequency, it is not that good. How I remember capacitor is not that good is you just remember capacitor is the one that used for charging. When it is charging, it is very, very slow to charge. So when you want it to charge fast, it needs to run a lot of time. So it needs to keep on running to catch up. That's why it is not good at high frequency. So before we go into the circuit again, we only do the prerequisites today. Some circuit theory concept. We can have circuit representation in terms of 2 types of domain. If you guys learn your year 3, so I suppose you will already run maybe Fourier series. So Fourier series, we are basically transforming from time series to frequency series to time series, Fourier series, Fourier transform. So at time domain, if you have a circuit V1 and C1, at time domain, you can model the I1. First, the current flowing in is C1. The derivative of V1 versus dt. Okay, so we differentiate V1 over dt. How much change of voltage times your capacitance, it will be your current. But at frequency domain, we don't call it C1 dV1 dt. At frequency domain, we will just change this change of t into S directly. So instead of C1 dV1 dt, we change it to C1 SV1 directly. So this is your frequency domain. Change of time is your frequency domain, so you call it S. Then your V1 over V1 over I1, sorry, it will just be 1 over C1 times S. So 1 over C1 times S, S is your J omega. So it looks like your impedance of your capacitor, that's it. At the same time, if it is time domain, we say that V1 is equals to R1 I1 plus with this, whatever current flows to here times 1 over C1, then it will be your V1 already. Okay, so all this current that flows through here, okay, current that flows through here, we say it is the derivative of your I1. So we move this I1 down. So it will just be in reciprocal of this whole thing. So you change into this term. Integral of I1 dt 1 over C1 is whatever happening over here. So the voltage drop over here plus the voltage drop over here equals to your V1. So finally, your V1 is equals to R1 C1 dV out plus V out. And then you again convert this into frequency domain. So this concept is just want you to know that you can always convert time domain into frequency domain in any way form. And their meaning will still be the same. When we consider S equals to J omega, we can find transfer function already. So we came up with this. V out is equals to 1 over C S divided by 1 over CS plus R1 times V in. We can find frequency domain, or what we can find transfer function. So what exactly is transfer function? Transfer function is what we exactly need to find in this chapter. Transfer function is output over input, but in relative to frequency domain. That's why we don't call it gain anymore. We call it HS. HS is your transfer function. It is V out over V in, but in frequency domain. So V out over V in frequency domain, it will be 1 over C1S divided by 1 over C1S plus R1. This is the whole term. And this term, if you just put this J omega, S equals to J omega, it will be 1 over 1 plus R1 C J omega. So this is the main transfer function from the circuit just now. Basically, when I say I want to find transfer function, you find what is the V out over V in. But in terms of frequency form. V out over V in terms of frequency form. Okay, I will give some time. You have a look at this part. You have to roughly understand this part first before we can proceed. Okay, take attendance. Two more people haven't signed.
Look, students. My name is wait, yeah, Hong Yusheng. Okay.
Okay, so I assume those that needs to sign already. Okay, we continue. I will roughly go through all this part quickly because I know you guys just want to focus on your quiz anyway. Make sure you do your assignment, that's it. And then once I quickly go through all the theoretical part, we will do some practices for quiz. Maybe quiz, it depends on you all. It can be week 13, week 14 also can. Because by that time you already finish your group assignment, your final project, you should roughly know what is happening in the circuit. Then that time we do the quiz. Okay, so before we go into that, we will still need to learn some prerequisites first. Okay, some prerequisite first. First of all, we know that complex number A equals to JB, it can be converted into magnitude and phase. If it is magnitude, it is just square root of A squared plus B squared. If you want the phase, it is tangent, inward tangent, B over A. So if we take this HS just now that we defined just now, 1 over R1 Cj omega, then the magnitude of HS, it will just be 1 over square root R squared C squared omega squared plus 1. So this is the frequency response. Two terms, just now we say you want to find transfer function, it is VR over V in. Frequency response is the magnitude of it. The magnitude of it. So the magnitude of it, here is where we define negative 3 dB. Last time during LT SPICE simulation, I told you all that we need to go down. Let's say your gain, AC gain is at negative 30 dB. I say that if you want to find the bandwidth, you need to say negative, you need to find the point where it is negative 3 dB. So it was 30 dB, then you need to minus 3. It becomes 27 dB. And you find which frequency that it can accommodate that 27 dB. So similarly over here, we call the negative 3 dB bandwidth. Okay, this, how does it coming from? It is actually, we assume R is 1, C is 1, omega is 1 at very low frequency when it is still working well. So 1 plus 1 equals to 2 over here. R squared, C squared, omega squared, everything equals to 1 already. Plus 1 equals to 2. So 1 over square root 2 is the point. So we think that this time still work. That's why we call it negative 3 dB bandwidth. And at this point, your frequency response is actually 1 over square root 2. 1 over square root 2, if you convert everything into dB, it becomes negative 3 dB. Here is how it is actually working. Okay, so the negative 3 dB is a standard. We call it effective bandwidth, where the circuit starts to roll off after this 3 dB. Next term is poles and zero. We call whatever thing, so we already have our transfer function. Transfer function VR over V in. So for sure we have numerator and denominator. So the one at the top, we call them the zeros. The roots of the top will be the zeros. The roots of the bottom part will be the pole. Okay, so how do we say when it is a roots? Roots mean when we take an S only, whatever on top only, and we say it is equals to 0. We find out what exactly is NS equals to 0. Then that is the root. So we call them zeros. When we take the bottom part equals to 0, we call them poles. So Bode's rule says that S of frequency, so your working mic or something, pass through a pole frequency, like I mentioned, the pole, the bottom pole, the slope of your transfer function, your frequency response, will decrease by 20 dB per decade. Meaning that it will be working very well, 30 dB all the way, until it see a pole in your circuit. Then it will drop by 20 dB per decade. Maybe some circuit have 2 to 3 poles. So whenever it see one pole, it will drop by 20 dB per decade. But at the same time, if the omega, your circuit pass through zero frequency, the slope will increase by 20 dB per decade. So here is the representation. If from the circuit, We do not know how to find pole and zeros yet, but we will figure out next class. But let's say we just assume that we found a pole. The circuit will have a pole, then it will have this characteristic. It will go slow, it will go steady, and then it will drop by negative 20 dB per decade once it saw the pole. Similarly, if it saw the pole, initially when it was still increasing one, but it saw the pole already, then it needs to drop by negative 20 dB per decade, right? So it will be a flat line because initially this slope was plus 20 dB per decade. I want to minus out the 20 dB per decade, the slope, so it becomes a flat line. Is this part understandable? When you see some pole, if it is a flat line, it was zero slope. So my slope needs to be negative 20, so I go negative 20, so it will go down. But if it was increasing by 20 dB per decade, now when I see pole, I need to minus 20 dB per decade. So 20 minus 20, it becomes a flat line. That's the general concept. But if I see a zeros, usually we don't see zeros much in circuit. So we focus only on the poles. But if you see zero somehow, it will go up by 20 dB per decade. Or if initially it's plus 20 dB per decade, you need to go up by 20 dB per decade some more. So it will be plus 40 dB per decade. Is that okay? I am not very sure, but it's okay. We will go through that more the next class. I think that's all for today because everything else is linked together. Yes, everything else is linked together. So that's all for today. We'll see next Friday. Yeah. Okay. Please do your assignment. So there's no final, so you don't need to attend classes, but please do assignment.